Hello. This video is going to talk about fluid pressure regimes. And what I mean by that is the fluid pressure that you encounter deep underground when an oil or gas field is first discovered. And what we're going to do is we're going to show how to do a calculation that can use measured pressures, because you measure the pressure when you drill the well, measure the pressure of the fluids, how you can use those measurements to determine the location of the contact between oil and gas and between gas and water. And that can give you some idea of the height of the oil column. And it is a key component of analysing a reservoir and actually finding out how deep it is. So to do this, what I'm going to do is use a whiteboard here that I have. So we have here essentially a screen that I can write on for you. Okay, so you can see I can write that. So what we're going to do on the left-hand side is I'm going to draw, first of all, a sort of schematic of a dome-shaped reservoir. So what we've got here is that this is your impermeable barrier, okay, and there's going to be an accumulation of hydrocarbon. Now, I'm drawing it like this so it's going to fit on the page. It is absolutely not to scale. The typical heights of an oil column are around a few tens of meters. The lateral extent, this distance, is typically kilometers. So this is quite traditional in geology, where you always have an exaggerated vertical scale. But in other disciplines, maybe it's a little bit unusual, but just bear that in mind. Okay, this is deliberately not to scale. But what I want to draw now is some axes that show on this axis is going to be pressure. Pressure is going to increase this way. So P for pressure. And on this axis, as we go down, okay, we're representing depth here. This is going to be depth, which I'm going to indicate with a Z. Okay, so this is depth as we go underground. And I'm going to look at fluid pressures. But we also know how fluid pressure varies with depth. We can write the following equation: dP dz is rho g. So rho is the density of the fluid. This can be oil, water, or gas. G is the acceleration due to gravity. P is pressure. Z is depth. So pressure increases with depth. Now there's a key point here. We're looking at fluid pressures. We're looking at the pressure of the fluid inside a porous medium. Now, this shouldn't be confusing, but sometimes you do need to think through it, because that pressure obeys that equation with the fluid density. You might say, well, if I'm a fluid in the micron-sized pore space, I can't sort of see above me, but that's true in this room. I can't see the sky above me, and yet the air is at atmospheric pressure. And the reason is because the air in the room is continuous with the air outside. You're not in an airtight room. It's going to be exactly the same when we're deep underground. We're in porous rock. Those pore spaces are connected. And so as we go down through the porous rock, the pressure in the fluid will vary as the density of the fluid times G times obviously the change in height. That is distinct from the pressure within the rock. So the rock itself, if we're inside the rock, that rock has a pressure, and that's essentially the weight of the rock above it. So typically a higher pressure because rock is denser. So there is a rock pressure and a fluid pressure, and those are distinct. The one I'm going to talk about, because I'm interested in fluids, is the fluid pressure. So let's start by considering the pressure of the water. Okay, so we can do this with a blue color here. Okay, so water is going to be the most dense phase, and so the pressure increases rapidly with depth. So I can draw a diagram that sort of looks like that, and that is the water pressure. Then what I can do is I can also have oil, which I can depict in green. Okay, and the oil pressure doesn't vary so much with depth. Okay, and I can also draw the gas pressure. Now, the way I've done it here is Now what I want to do is I want to move that so that I can move that here. Okay. I can move that here. Okay, like that. And I can get a black pen again. Right. So what we have here is I can do in a dotted line here. Okay. I go along here. Okay. Here we can have the reservoir. Down here we have water. Okay. Here we have oil. And here, right, we have gas. And the way I've drawn it is that this is the top of the reservoir. So here it's all an impermeable barrier to flow. Okay, so this is impermeable rock. Here we have gas, oil, and water. And the equation here, this is an equation of a line showing the water pressure, the oil pressure in the oil column, and the gas pressure in the gas can. Now, you might say, first question is, well, why is the water here? Why do I continue this line all the way? And the reason is, okay, this may be impermeable, but the water may also be continuous all the way around here. So there'll be other rock that's saturated with water here, and it can be in pressure equilibrium with the water here. So in fact, there is water outside the reservoir. There is also water within the reservoir, and that's actually rather important. There's also, although there's gas and oil here present in the pore space of the rock, there will also be water present. So it's perfectly legitimate for me to draw a line. So now let's write down some equations. We've got this. So now what are we actually doing when we discover a field? So we can imagine that we drill a well through my reservoir like this. And what I could do is, as I'm drilling the well, I can measure the depth. I know how deep I've gone. I can call this, for instance, Z1, and the pressure that I measure in the water at that location I can call P1. Okay? And I can also imagine that as I'm drilling my well, I contact oil. I know it's oil. I've got my log measurements. I can even extract a sample of oil to analyze it in the laboratory, but I can also measure the fluid pressures. So we can measure the fluid pressures and imagine that at this depth, which is a shallower depth, Z2, I've measured a pressure P2. And the final one, I can imagine that I've measured a pressure Z. Great, okay. So that's a schematic, okay, of how I've measured the pressures. Now, what's interesting about this is if we know the density of the phases, and we do because we can extract a sample of the fluids, we know the densities, you can sort of see almost geometrically that it's possible for me to see where the contacts are between the gas and the oil and between the oil and the water. And in particular, what's of interest to me if I have an oil field is the height of the oil column. What depth in the subsurface do I encounter? And that can be used to calculate how much oil I have underground. I need to know some other properties that we're going to talk about later. But clearly with a seismic survey, when I take sound waves down through the rock, that can sometimes identify the location of these impermeable barriers. So I get some idea of the structure and sort of the extent, but I don't know how much there is in terms of the oil. Now you might say, well, just a moment, but I've seen the previous presentation and surely you can do this with log measurements. I can instead, as I'm doing down here, I can look at density. The density changes as I go from gas to oil. The resistivity will change when I go to oil and water. So I can see those contacts from the logs. But very frequently, actually, maybe there was a problem with the log measurements. Maybe you had a well that, say, came in here and just encountered water. Maybe you had another well that, say, came in here, right, and only encountered the oil, and then you had to stop drilling. So there are lots of examples, and also you can think about the geological structure being different. You can actually drill straight through the oil column, but you don't actually see the contact either with water or gas. So there are lots of cases where you don't necessarily. And even if you do, one thing about petroleum engineering is you're looking at complex things deep underground. You don't know for sure what's happening. And so you need to look at different pieces of data. So don't throw away a piece of data. So this is going to give you information, and in particular, it's going to give you the information of where the oil and water have the same pressure. And I can call this the free water level. FWL, and this can be called the free oil level. Free oil level. Okay, so now let's write down some equations. So I can write down the pressure for the water. Okay, if I look at this, the water pressure is going to equal. Now I can integrate the equation above, but right, that should be hopefully relatively straightforward here. I can integrate the equation that was above here, right, this equation with rho W, okay, and I also know that at Z equals Z1, P equals P1, so this disappears and P equals P1. So if I differentiate it, I get this, and I put in the measured value, so that hopefully that equation makes sense. And now I can write quickly, I'm not going to spend too much time on it, I can write the equation for the oil pressure as well. The oil is P2 plus rho oil G Z minus Z2. And then I can write a final equation that is for the gas. Maybe write it here, Pg is equal to P3 plus rho G Z minus Z3. Okay, so those are the three pressures. And now what we want to do is we want to find the locations of these free water levels. Okay, and we know that those locations by definition, okay, are where the two pressures are the same. So the free water level is where the water and the oil pressures are the same. The free oil level is where the gas and the oil pressures are the same. And then the difference between those are going to give me the height of the oil column. And because I want to keep the equations here and we don't have a huge amount of space, what I'm going to do is I'm actually going to erase my little cartoon of the oil reservoir, but hopefully you can sort of understand where that comes from. Okay, and I'm going to now write the equations here. So for the free water level, I know that P2 is P1, or P oil is P, sorry, not P2 is P1, the oil and water pressures are the same. So I can write for the free water level P1 plus rho WG, and then I've got Z of the free water level minus Z1 is equal to P2 plus rho naught G, Z of the free water level minus Z2. So I've just basically put these two equations to be the same. Okay. So then what I can do is I can rearrange those equations again. You know, if you can see this easily, fair enough. If not, rather than just following what's on the board, you know, try and do it yourself. So I can now write down an equation, and I'm not going to go through too much algebra here, but Z of the free water level, okay, the density of water is greater than that of oil, so I'm going to collect the terms over this side. So what we have here is on the top, we've got P2 minus P1 plus rho WG Z1 minus rho oil GZ2. That's all going to be divided by rho W minus rho oil G. Okay. So that's the first major result. Okay, so that tells me from two pressure measurements. So drilled a well, I've measured pressure in the water, I've measured pressure in the oil. If I know the density of those fluids, then I can find a simple equation and I can find the free water level where those two pressures are the same. Okay, I can do the same with the gas. One question you might say about the gas is, how do I know the gas density is constant? Of course it isn't. It will vary with pressure. So I'm making an approximation here. I'm assuming quite a small gas column, so that the gas density doesn't change much. Also, remember, we are deep underground at very high pressures. Okay, so at those high pressures, the gas isn't necessarily super compressible. Okay. So we can go through exactly the same type of calculation where the free oil level is when the gas and the oil pressures are the same. And rather than go through the algebra, because I simply don't have much room on here, I'll just write the equation here. So free oil level, okay, is going to be P3 minus P2 plus rho naught GZ2 minus rho GZ3. And this is all going to be divided by rho oil minus rho G. And then the height of the oil column, which is sort of what we want to know, is going to be the difference between them. The depth of the free water level is the larger number minus the depth of the oil level. Okay, so that gives you the height. And on this diagram, that's what H is. Right? It's the difference between those two. Okay, so that's a calculation you can do. You will see in the notes all the equations are there, and there are plenty of exam exercises where you can practice essentially calculating those. I tend to do things, as I said, tend to do the calculations in SI units. As you'll notice, there's no unit conversions here. So this is all done in SI units. So pressure here will be measured in pascals, rho in kilograms per cubic meter. G is 9.81 meters per second squared. Z is a distance in meters. The only thing to bear in mind is don't be silly about units. P is often quoted in megapascals. Well, you need to convert that to pascals. Don't get mega and other things confused. They try and make sure that everything is done strict SI. Sometimes people get a bit confused with this. They think they're doing petroleum engineering and they know that we use funny units. So they think when we do SI units, we don't do them properly. And then you get yourself into a complete muddle. Okay, so this is the first calculation. It enables you to calculate basically the height. Now, there are a few things we can say now immediately. The first one that's rather interesting, if we look at this, is here on the diagram, we have the water pressure. And you'll notice at a given depth, the pressure in the oil and the gas are higher. Now, it's not just that the oil and gas are deep underground and they are at a high pressure. But if I was drilling a well and water just naturally was falling into the well, okay, so in the well, I would be following a pressure that's essentially this line. The gas and the oil are at a higher pressure, so they'd want to move into the well. Now, sometimes people even think that's counterintuitive because they say, but gas and oil are less dense than water, so they must have a lower pressure somehow. But no, that's not correct. What you've done is you've held the oil and gas underground. There is a point deep where the pressures are equal. As I go up, the oil and gas pressure varies less than the water pressure. It's at a higher pressure. And the way of thinking about this is essentially these fluids are buoyant. Okay, oil and gas are buoyant. I can write that word down because it has a strange spelling even by English standards. Okay, so the hydrocarbons are buoyant. And what do I mean by that? Well, imagine you have a bath and you've got a balloon. Okay, and the balloon's full of air, so you know that the air hasn't much density. Now imagine that you try and push that balloon under the water. And that's what you see here. The oil and gas are deep underground, surrounded by water. Now, you get that balloon in, try and push it, it comes up again. Really, if you really push down hard, you can keep the balloon underwater. So the balloon, the air in the balloon has a lower density than water, but it's at a higher pressure because it's pushing back on you. Why is that? Exactly what's shown here. At the bottom of the bath, okay, you have an equal pressure. At the top of the balloon, because the air has a low density, it has a higher pressure than the water, and it seems to be pushing up. It wants to go up. And in fact, that's the case. In an oil reservoir, the reason why the oil isn't escaping to the surface is the cataract rock is holding down the oil and gas. Okay. So in many ways, that looks good for production because you drill a well, the oil and gas naturally will want to move into the wellbore, but it's highly unsafe. So what is called in petroleum engineering a blowout, okay, is where you have an uncontrollable release of oil and gas. So if I were to just drill a well and allow water to be in the well, and I'm drilling and the water's circulating and getting rid of the cuttings, when I encounter a hydrocarbon, that hydrocarbon is at a higher pressure, it will move very rapidly into the wellbore, and there will be a sudden release. And of course, once it's in the wellbore, then what's in the well is less dense, and so there's an even bigger pressure difference, and it just escapes outwards. And that, as I said, is extremely dangerous. You want to avoid a blowout. Okay? So how do you do this? Well, I mentioned in the previous lecture, you have a blowout preventer that will slice the wellbore, but seeing as how you normally pay tens, if not $100 million for your well, that is a last resort. What you want to do is you want to do it in a controlled fashion. And the way in which you do it in a controlled fashion, and we mentioned this already, is you have what's called a drilling mud. Okay? Now, we mentioned drilling mud before, drilling mud being something that it's a D there, so it's got a bit truncated. A drilling mud is something that would lubricate the bit, carry away the cuttings, keep it cool. But the main thing about a drilling mud is that it's dense. Okay? It's a dense fluid. Okay? So it's dense. So what does that mean in this diagram? It means that if this is the surface here, and I have a high density fluid, then my drilling mud that I can say maybe in a brown color, but as I said, it's not a mud, it's a technical expression, or a dense fluid. I want to have a denser fluid, so pressure varies more rapidly with depth, so that when I get to the hydrocarbons here, the fluid is at a higher pressure. That's safe, because now when I encounter the hydrocarbons, the mud will move into the formation, but nothing will come out. So that's safe. It prevents a blowout. Okay. So what do you do to make the fluid dense? You normally have what's called barytes, barium sulfates. These barytes are very dense. They simply make a dense mixture, and this can be dissolved, as I said, in either water, as I said before, either water or oil. So you have these barytes that make the dense fluid. The problem with this, however, is if this is a higher pressure, what you tend to do is now the drilling mud gets forced into the formation, which wastes money because you're losing the mud, but also it contains all the cuttings, and so it tends to clog up the formation. So ideally, you want to have a mud that is just about this pressure, so it's both safe, but without a big pressure drop that's clogging up the formation. The final thing I want to say in this sequence is about these free water levels, in that they're technically the free water level, not what's called the oil-water contact. And let me explain the difference. So again, I want to give myself a bit of room here. Okay, so I'll erase these equations. As I said, these equations are all in the notes. What I label 1, 2, and 3 may be different, but you're supposed to understand, the concept here is hopefully you find it reasonably straightforward and are able to do the calculations. And that's what you have to do. So now, if I look here, if I talk about the oil-water contact, it's normally given this, let's go with black. So oil-water contact. Right? The oil-water contact, right, is where we first, or the depth, basically the deepest depth, where we see significant oil in the pore space. Now this contact, the oil-water contact, typically may be slightly above the free water level. You might say, well, why is that? That's a bit strange. Why do we see it above the free water level? So let me explain, and I'm just getting rid of some of the extraneous material here that we don't need anymore. Okay. So why is the oil-water contact above the free water level? And it's due to capillary pressure. And capillary pressure is in fact defined, PC, P for pressure, C for capillary pressure, is the difference in pressure between oil and water. And you can also have a capillary pressure between oil and gas and water as well. Okay, so this is just the oil-water capillary pressure, but any pressure difference is capillary pressure. Okay, so what do I mean by this? So initially, before any hydrocarbon has entered my reservoir, I have rock, this porous rock, that's fully saturated with water. And this rock may be silica, so like glass, calcium carbonate, so like chalk. These are sort of ionic surfaces. Water, as you know, has hydrogen bonding. The water actually likes the surface of the rock. Oil comes in. Oil is a non-polar substance. The oil doesn't like being next to the solid surface. So in order to get the oil into the rock, you actually need a pressure. You need the pressure in the oil to be higher than the water. The oil doesn't like being in the rock. It has to be forced in. So what you find is at a depth where the oil and water pressure may be the same, actually, it's a bit of a theoretical concept because the oil can't get in the pore space. It can't squeeze its way in. There needs a finite capillary pressure. So you notice here, the oil pressure is higher than the water pressure. There is a capillary pressure, EC, a pressure difference. That is a finite number that is needed so that the oil can enter the rock. And so when we look at the contacts, which are actually measured, from resistivity, where we go from a lot of water to not much water, that would tend to be a little bit higher. And when I say a little bit higher, normally, about a meter or two higher than where the two pressures are normally the same. As I go further up, the capillary pressure actually increases, right? It increases delta rho g h, where h now is not this h, it's a distance above the free water level. So what happens then, what that means is the oil's at higher and higher pressure and can squeeze into more and more and more of the pore space. So as we go above the free water level, to begin with, often we don't see any oil, then we begin to see some oil, and then more and more and more oil is squeezed into the pore space. And we would see something similar with gas, in fact. Here, because gas and oil have rather more similar properties, the difference between when you actually see gas and the free oil level is normally quite small. And again, you have gas squeezing into more of the pore space, but you can see that the gas water capillary pressure, the difference in pressure between gas and water, is now quite high. So near the top of the reservoir, the gas has basically squeezed the water out. The water's just clinging in some of the small pores or near the surface of the rock. So that concludes what I wanted to say about pressure analysis. So I'll pause here. My recommendation, if you're following this video, is also to read the lecture notes and also then to try some of the practice questions when you're asked to calculate the depths of these free oil, free water levels, the height of the oil column, estimate how much oil is in place, and then make some commentary on those numbers. Okay, so I'll stop here. Thank you very much.